Hi guys, Dr. Colbreth here with an example problem for the hydraulic lift. And it says a 55 kilogram cheerleader uses an oil-filled hydraulic lift to hold 410 kilogram football players at a height of 1 meter. If her piston is 16 centimeters in diameter, what is the diameter of the football player's piston? All right, so we have a hydraulic lift, the cartoon of which looks like this. We're told that the cheerleader stands in a piston that has 16 centimeter diameter. And we have how many football players? 4 football players. 1, 2, 3, 4. And we're told that this height right here is 1 meter. And it's oil, so the density of oil is equal to 900 kilograms per meter cubed. And the mass of the cheerleader is equal to 55 kilograms. And the mass of each football player is equal to 110 kilograms. So, as with most hydrostatic problems, we're going to consider the pressure at the same height in 2 different regions of our hydraulic system. So the pressure at A is going to be equal to the air pressure plus the pressure due to the cheerleader, which is going to be that force, which is the mass of the cheerleader times G, divided by we'll call this area over here area 1. We'll call this area over 2 area 2, divided by area 1. And the pressure at B is going to be the air pressure plus the pressure due to the force of the football player. So that's going to be 4 times the mass of the football player times G, divided by its area, area 2. And then we also have the weight of the fluid above point B. So that's going to be plus rho times G times H, where in this case H is 1 meter. So because we have chosen point A and B along the same horizontal line, we can set the pressure at A equal to the pressure at B. So on the left-hand side we get P0 plus the mass of the cheerleader times G divided by area number 1, which is going to be pi times R1 squared. That's going to be equal to air pressure plus 4 times the mass of the players times G divided by pi times R2 squared. This is the quantity that we're looking to solve for. We know what R1 is, plus rho times G times H. So we have that the air pressures cancel. Now we have a G in every term, so we can lose those 2. And we end up with the mass of the cheerleader divided by pi R1 squared is equal to 4 times the mass of the football player divided by divided by pi R2 squared plus the density of the oil times the height. Okay, let's subtract this from both sides. So we get the mass of the cheerleader over pi R1 squared minus rho times H is equal to 4 times the mass of the player divided by pi R2 squared. So I'm going to multiply both sides by pi R2 squared. And I am going to divide both sides by this whole term in the parentheses here. So on the left-hand side, that's going to give me pi R2 squared. On the right-hand side, that's going to give me 4 times the mass of the players divided by the mass of the cheerleader divided by pi times the R1 squared minus rho times the height. All right, so that gives us that R2 is equal to the square root. I'll go ahead and pull a 2 outside. The mass of the football player divided by the mass of the cheerleader. We have a pi to multiply through, divided by R1 squared minus rho times pi times H, which is equal to 2 times the square root of the mass of the football player was 110 kilograms, divided by the mass of the cheerleader was 55 kilograms, divided by R1 squared. So R1 was 8 centimeters. 8 centimeters, so this is going to be 0.08 meters squared, minus rho, which we said was 900 kilograms per meter cubed, times pi times h, which is 1 meter. Plugging all of this into our calculator, we get that R2 is equal to 0.276 meters, or that the diameter of the second cylinder is equal to about 55 centimeters.